Dear students, welcome back to the lecture series in Module 2 Elasticity chapter. In this class, we are going to study three important derivations which are very important for examination. First one is expression for the torsion of a cylindrical rod, and ultimately we are going to derive an expression for torque or couple. See the diagram. We have a cylindrical structure here. Consider a long body which is twisted around its length as an axis, which is said to be under torsion. This twisting is brought into effect by fixing one end of the body to a rigid support and applying a suitable couple at the other end. The elasticity of a solid, long, uniform cylindrical body under torsion can be studied by imagining it to be consisting of concentric layers of the material of which it is made up of. The applied twisting couple is calculated in terms of the rigidity modulus of the body. Next slide. Consider a long cylindrical rod of length L and radius capital R, which is rigidly fixed at its upper end. Let O' be the axis of the cylinder. Imagine the cylindrical rod is made up of thin concentric hollow cylindrical layers, each of thickness dr. The rod twisted at its lower end, and then the concentric layers slide one over the other. This movement will be zero at the fixed end and gradually increased along the downward direction. Let us consider one concentric circular layer of radius r and thickness dr. Consider any point x on its uppermost part, which would remain fixed, and a point like B at its bottom, which moves to B'. From the diagram, angle BXB' is equal to phi, which gives the angle of shear. Since phi is also small, the moment length BB' can be equated to L into phi. Also from the diagram, you can see that angle BO'B' is equal to theta, and hence the length BB' is equal to R into theta. Equating the two, we get L phi is equal to R theta. Now, the cross-sectional area of the layer under consideration is 2 pi R dr, and if capital is the shearing force, then the shearing stress T is given by T is equal to force by area, which is equal to F by 2 pi R dr. Therefore, shearing force F is equal to T into 2 pi R dr. We know that rigidity modulus N is equal to shearing stress divided by shearing strain, that is N is equal to T by phi. Therefore, T is equal to N into phi, that is equal to N into R into theta divided by L. That is by substituting the value of phi. Therefore, equation for F becomes equal to N into R into theta divided by L into 2 pi R dr, or we get 2 pi N theta by L into R square dr. Therefore, the moment of the force about O' is equal to force into distance, that is 2 pi N theta divided by L into R square dr into R, which is equal to 2 pi N theta divided by L into R cube into dr. This is only for the one layer of the cylinder. Therefore, twisting couple acting on the entire cylinder is obtained by summing up or integrating the above equation, which is equal to integral 2 pi N theta divided by L R cube dr, where R varies from 0 to capital R. that is equal to 2 pi n theta divided by L into r to the power 4 divided by 4 ranges from 0 to r. We get pi n r to the power 4 divided by 2L into theta. Couple per unit twist is given by C is equal to total twisting couple divided by angle of twist, that is equal to pi n r to the power 4 theta divided by 2L divided by theta, or we get C is equal to pi n r to the power 4 divided by 2L. Remember this equation. Numerical problems can be asked based on this equation. Next important derivation is to obtain an expression for Young's modulus in the case of a single cantilever. First, let us see what is meant by a single cantilever. If one end of the beam is fixed to a rigid support and its other end is loaded, then the arrangement is called single cantilever or simply cantilever. Consider a uniform beam of length L fixed at M, that is in the left side. Let a load W act on the beam at N, that is in the rightmost side. Consider a point on the free beam at a distance x from the fixed end, which will be at a distance of L minus x from N. Let P1 be its position after the beam is bent. P1 or P dash, we will take P dash. Okay. Therefore, bending moment is equal to force into perpendicular distance, that is equal to W into L minus x. So, we have denoted force by W, and actual value of W is given by product of M into G. But bending moment of a beam is given by Y by R into Ig. In the earlier derivation, we have seen this. Therefore, equating Y by R Ig is equal to W into L minus x, or 1 by R is equal to W into L minus x divided by Y into Ig. But if Y is the depression of the point P, then it can be shown that 1 by R is equal to d square Y by dx square, where R is the radius of the circle to which the bent beam becomes a part. Comparing the above two equations, we can write in place of 1 by R we can substitute d square Y by dx square, which is equal to W into L minus x by Y into Ig. That is, d by dx of dy by dx is equal to W into L minus x divided by Y into Ig, or d of dy by dx is equal to, taking dx into the right side, we get W into inside the bracket L dx minus x dx divided by Y into Ig. Now integrating both sides, we get dy by dx, which is equal to W by Y into Ig into Lx minus x square by 2 plus C1, where C1 is the constant of integration. As you see, dy by dx is the slope of the tangent drawn to the bent beam at a distance x from the fixed end. When x is equal to 0, it refers to the tangent drawn at M, where it is horizontal. Hence, dy by dx is equal to 0 at x is equal to 0, x is equal to 0. Introducing this condition, we get C1 is equal to 0. Therefore, we can write dy by dx is equal to W by Y into Ig into Lx minus x square by 2, or dy is equal to W by Y into Ig into Lx minus x square by 2 dx. Again integrate, we get Y is equal to W by Yig into Lx square by 2 minus x cube by 6 plus C2. Once again, using the boundary condition, we can show that the constant C2 becomes 0. Hence, we get Y is equal to W by Y into Ig into Lx square by 2 minus x cube by 6. Let us consider the loaded end. Y is replaced by Y0 and x is replaced by L, because L is the length of the cantilever. We get Y0 is equal to W by Y into Ig into L cube by 2 minus L cube by 6, and simplifying, we get depression produced at the loaded end is Y0 is equal to WL cube divided by 3 into Y into Ig. Therefore, the Young's modulus of the material of the cantilever is given by, once again rearrange this equation, Y is equal to WL cube divided by 3 Y0 Ig. First case, if the beam is having rectangular cross section whose breadth is b and thickness is d, then moment of inertia Ig is equal to bd cube by 12. Substituting this in the previous equation, we get y is equal to wl cube divided by 3y0 into 12 by bd cube, or we get y is equal to 4wl cube divided by y0 into bd cube. Second case, if the beam is having a circular cross section of radius r, then Ig is given by pi r to the power 4 divided by 4. Substituting the expression for moment of inertia Ig in the previous equation, that is the expression for y, we get y is equal to 4wl cube divided by 3y0 pi r to the power 4. Consider a front face of a cube ABCD whose lower surface CD is fixed to a rigid support. Let a tangential force F is applied at the upper surface along AB of the cube in a direction as shown in figure. The applied tangential force causes the relative displacements at different parts of the cube so that A moves to A dash and B moves to B dash through a small angle. Due to this, the diagonal AC will be shortened to A dash C and diagonal DB will be increased to length DB dash. Let theta be the angle of shear, which is very small in magnitude. Let L be the length of each side of the cube. Then AA dash is equal to BB dash is equal to L. As theta is very small, from triangle BCB dash, we can write theta is equal to tan theta, that is equal to L by capital L. As diagonal DB increases to DB dash and diagonal AC is compressed to AC dash, we have extension strain along DB and compression strain along AC. Therefore, extension strain along DB is equal to NB dash divided by DB. If the length of each side of the cube, then from triangle BCD we have DB is equal to square root of 2 into L. From triangle BNB dash we get NB dash is equal to BB dash cos 45, which is equal to L by square root of 2. Therefore, elongation strain along DB is equal to NB dash divided by DB, that is equal to L by root 2 divided by capital L into root 2, that is equal to small l divided by 2L, which is equal to theta by 2. Similarly, the compression strain along AC is equal to MA dash by CA, which is equal to MA dash by CA, which is equal to L by root 2 divided by capital L by root 2. We get L by 2L, which is equal to theta by 2. From above equation, it is clear that a simple shear theta is equivalent to an extension strain and compression strain at right angles to each other, and each of value theta by 2. The converse is also true, that is simultaneous equal compression and extension at right angles to each other are equivalent to shear. Thus, elongation strain plus compression strain is equal to theta by 2 plus theta by 2, which is equal to theta, the shearing strain.